Okay, so let's take a look at section 2.5. We're going to skip the warm-up. Let's come down to deriving the equilibrium expression. All right, we have this reaction at equilibrium. And if we're looking at the forward rate, so this right here, that little R sub F, this is the forward rate. And then the same reaction over here, this is the reverse rate, okay? And at equilibrium, doesn't the forward rate equal the reverse rate, okay? So if you substitute this for the forward rate, and you substitute this for the reverse rate, and you rearrange that equation so that you isolate the constants on one side, we can replace the forward rate constant divided by the reverse rate constant with something called KEQ. And we call this the equilibrium constant, okay? So you see that down here. The equilibrium constant is equal to the concentration of the product raised to the power of its coefficient divided by the concentrations of the reactants multiplied by each other raised to the power of their coefficients, okay? And if we go on to the next page, regardless of what the initial concentrations of reactants and products are, when equilibrium is achieved, the equilibrium concentrations can actually be substituted into that equation, and you can use them to calculate the value of KEQ, okay? And it'll be the same at any temperature. So the equilibrium constant KEQ is temperature dependent, okay? And the equilibrium expression is the formula for the equilibrium constant in terms of the equilibrium constants of reactants and products, okay? So that's what was written on the previous page. And the equilibrium constant is the numerical value that's provided by substituting those concentrations in at equilibrium. Okay, so the equilibrium law tells you that if you have the balanced chemical equation, you can write the equilibrium expression, which is this, okay? And P, Q, R, and S are the coefficients from the balanced chemical equation. Those are the exponents that you will use. And the equilibrium expression and constant are independent of whatever mechanism is taken in a balanced chemical equation, okay? So what I'm gonna do is I'm gonna jump ahead to practice problems on the next page, and we're gonna take a look at how to do this. So let's go right here. So here it says that we've got these gases at equilibrium. They gave us the concentration of hydrogen, iodine, and HI. And they want to know what the equilibrium constant is for the reaction at this temperature. So we need to write the equilibrium expression. So take the product, H2 times I2, divided by the reactant, HI, and raise it to the power of its coefficient. So this coefficient became an exponent right here. Now we're going to substitute in our concentrations. So H2 is 4.56 times 10 to the negative third. I2 is 7.4 times 10 to the negative fourth. And then HI is 1.35 times 10 to the negative 2. And that gets squared. When you put this into your calculator, you're going to end up getting 0.019. I'm just rounding it to 2 sig figs, since 2 sig figs was the fewest that we had. Okay, any questions for me on that one? The rate constant, if you turn back to the previous page, this rate constant, like this is the rate constant for the forward reaction. Do you know what I'm saying? I'm sorry, this is the rate of the forward reaction. That's equal to the rate constant for the forward reaction times the concentration of reactants. Whereas this equilibrium constant down here comes from the ratio of the concentration of your products over reactants raised to their coefficients at equilibrium. So does it factor into the equilibrium constant? Does what factor in? The equilibrium constant, is it? You mean like the K value from the forward or the reverse? So that K, those K values, you could think of it as that ratio is your equilibrium constant. Okay? Okay. So let's take a look at number 2. We've got 3.88 times 10 to the third molar NO2, and this concentration of N2O4. Here's your overall equation. They want to know what the equilibrium constant is at that temperature. Okay, so you will take the concentration of N2O4, divide it by the concentration of NO2, raise it to the second power because the coefficient in front of the NO2 is a 2. Okay, and then we're going to substitute everything in. So this is 1.73, and then 3.88 on the bottom. Okay, and then this is going to end up giving you 11.5, and I just rounded it to 3 sig figs because that was the fewest sig figs that I had in the problem. Easy? Okay, let's do part B. Part B wants to know if the reaction is endothermic or exothermic by comparing it with the equilibrium constant for the same reaction at 60 degrees Celsius to the constant 92 degrees Celsius, and that was given in a sample problem on the previous page. So why don't we take a look at the sample problem on the previous page. So if you take a look down here, here's the sample problem. They told us that we are at 92 degrees Celsius, okay? And that your KEQ is 4.4. So I'm gonna write this stuff over in 2B just so we have it. So over here at 60 degrees Celsius, the KEQ value was 11.5, okay? And then at 92 degrees Celsius, the KEQ value was 4.4, okay? Okay, so at a higher temperature, the equilibrium constant decreased. And this means that there must have been some sort of a shift. There must have been a shift to the left because your KEQ value came down. Do you understand what I'm saying? Ish? Okay. So if at lower temp, the KEQ increased, this means we have an endothermic reaction because heat or kinetic energy was removed causing the KEQ to increase, and that's because we made a shift to the right. So the forward direction is exothermic, okay? I'm sorry, exo. Did I say exo or endo? I don't remember. Okay, so as the temperature went down, we were removing heat. You notice that the equilibrium constant went up. And that's because it goes up because now you have a higher concentration of product. Okay, and then if you shift to the right, you're gonna bring back some of that heat which was lost when the temperature went down. Okay, okay, let's take a look at number 3. For number 3, you've got this concentration of NH3 at equilibrium with that concentration of N2. They want the equilibrium concentration of H2. Okay, so, oh, and they gave us the equilibrium constant, and here's your overall reaction. Okay, so what we're gonna do is KEQ is equal to the concentration of NH3 squared because of the coefficient in front of NH3 times N2 times H2 cubed. This value here is gonna get substituted in for KEQ, right? So this is 1.7 times 10 to the second equals 0.14 squared over 0.020, and then we're going to solve for H2. So I would just multiply both sides by 0.020 to cancel it there. And then this is 3.4 over H2 cubed, right? And then you could also multiply by H2 cubed to get this in the numerator over here. And then I would divide both sides by 3.4. And then I would raise it to the 1/3 power to cancel that. And that's going to end up giving you 0.18 molarity. Okay? Yes. If you what? cube root it. Yeah, it's the same thing. Okay, now let's take a look at what does a bigger equilibrium constant mean, okay? Let's come down here. The size of the equilibrium constant indicates the extent of the reaction's progress towards products. So the further a reaction progresses to the right to achieve equilibrium, the greater the equilibrium constant will be, okay? Be careful not to attempt to infer too much from equilibrium constants. So let's go to the next page. So it is impossible to infer anything about an equilibrium's position solely from the equilibrium constant. So the position depends on the initial reactant concentrations and the equilibrium constant. So if you have this reaction here, with this value for its equilibrium constant, okay? If the initial concentration of acetic acid is 1 molar, then there's a 0.42% yield at equilibrium. But if the initial concentration is 1 times 10 to the negative 6 molar, there's a 95% yield at equilibrium. So when they diluted it, it causes it to shift to the right to partially restore the osmotic pressure since this is in solution, okay? So that's one example. The other example is with the same initial reactant concentrations, it is difficult to make meaningful comparisons between equilibrium constants of different equilibria unless the expressions have identical forms. So I would underline the unless. Okay, so here we have got two different reactions at equilibrium, okay? And they have equilibrium constants of 1 each, okay? So they have much different percent yields even though they have the same equilibrium constants, which are at different temperatures, and the same initial reactant concentrations, okay? So this first equilibrium can have a greater KEQ than the second one, but still have a lower percent yield. Whereas if the concentration is 1 molar, there's a 23% yield. If the initial concentration of NO in the second equation is 1 molar, there's an 83% yield. So it doesn't matter that both of their values are 1 for the equilibrium constant. You just can't make an assumption, okay, because they aren't the same equilibria. Okay, let's go down here to, does an equilibrium constant change when the equilibrium system shifts? Okay. Changing the temperature is the only way to change a chemical equation's equilibrium constant. Okay, you'll notice in the table down here, when they add a reactant, the equilibrium constant does not change. If they decrease the volume, the equilibrium constant also does not change. But if they decrease temperature, the equilibrium constant suddenly changes. So this is what is important here. Okay? Let's take a look at the quick check on the next page. Consider the following equilibrium. In what direction will the system shift if some ammonia is added to it? Left or right? Yeah, there's your ammonia there as a reactant. So we're going to shift to the right. How will this affect the equilibrium constant? Well, does changing the amount of reactant change the equilibrium constant in the table on the previous page that I highlighted? No. So there is no change, okay? Consider the following equilibrium. A decrease in temperature will cause the equilibrium system to shift in which direction? Well, you've got heat energy going in as a reactant. So isn't this an endothermic process? So if I'm decreasing temperature, I'm removing some of that reactant, right? So I need to bring some of it back. So I'm going to shift to the left. What does that cause the percent yield to do? Yeah, decrease. And the equilibrium constant, which is affected by temperature, will also do what? It will decrease because we shifted to the left. Okay? All right, true or false? So we're going to look at this equilibrium here. We know that reactants are favored in this reaction because the KEQ is less than 1. Can you adequately infer that simply from the value of the equilibrium constant? Look at number 1 on the previous page. It says no. No, this is false. We can't. Because the equilibrium's position depends upon whatever the initial concentration of reactants were and the equilibrium constant value. Okay, let's go on to the next section. No liquids or solids in equilibrium expressions. Okay. So liquid or solid states are not included in equilibrium expressions. So if you take a look here, I have NaCl solid. It is not included in this equilibrium expression. The concentration of a pure solid or liquid is fixed by its density, while the concentration of a solute is not. Okay. I think the same sort of thing applies. Let's highlight this liquid down here. Increasing the surface area of a solid, it may increase the rate of dissolving, but it does not affect the equilibrium concentrations because the rate of recrystallizing is going to increase at the same time. So that's one of the reasons why we don't include solids. So a solid surface area, although affecting the rate at which equilibrium is achieved, does not affect the equilibrium position, okay? Adding or removing solids from an equilibrium affects the forward and the reverse rates the same. That's why you don't see some sort of a shift. If we're looking at liquids down here, H2O liquid is not included in any equilibrium expression. Water's concentration is nearly constant, so that's why we omit it. There is one situation where liquids appear in equilibrium expressions. when there is more than one liquid in the chemical equation. Those liquids dilute each other, so they are included, okay? Okay, let's go to the next page. And let's take a look at the quick check here. Write the equilibrium expression for the following reactions. Okay, so right off the bat, that solid is out, this liquid is out, and this solid is out. Okay.
Wait, I have a question.
I have an answer.
On the previous page, it says the H2O liquid is not included in any equilibrium expression. So is it only like a gas that, yeah.
Yeah, it's a gas, so that's why we include it there.
Okay.
In here.
Okay. Cool. Thank you.
You're welcome. Actually, did I mess up? No, those are gases, right? Yeah, they're gases. We're good. We good? Okay, let's go on to the equilibrium constant in the form of the chemical equation. So when you're looking at this reaction here, okay, the KEQ value is 3. But what if I take that same reaction and we double the coefficients? So this got multiplied by 2, okay? You'll notice that your KEQ value went to 9. So that means when you double the coefficients, you're going to end up squaring the constant. So the KEQ was squared. So doubling a chemical equation's coefficients has the effect of squaring its KEQ. What happens if I reverse the order of the original equation? So this equation here was reversed, okay? Then what happens to the KEQ value? So this KEQ value was inverted, so it's 1 over that KEQ value, okay? Let's take a look at the quick check. Here's the reaction, here's our KEQ value. What they did was they took the reverse of the original equation. So that means you're going to do 1 over the KEQ value, which is 1 over 0.018. And this ends up being 56. Okay. Here, they divided that equation by 2. So that means you would need to take the square root of the KEQ, which is 0.018, and this is 0.134. Okay. And then here, they reversed the original and they divided it all by 2. So what that means is you would take 1 over 0.018, and then you would, I need my calculator. Then you would take the square root. So you would do this first, which is 56, and then you would take the square root. And you're going to get 7.48. I'm going to make it 7.5. Okay? You could. Uh-huh. Okay, now let's go on to the reaction quotient here. When we have any value of reactant or product concentrations, and we don't know if we're at equilibrium or not, but we need to test it, then we're going to plug those values into the equilibrium expression to see if it is at equilibrium. And this is known as the trial KEQ or the reaction quotient Q. They mean the same thing. So this tells us whether a reaction is at equilibrium or not, okay? If not, the reaction will proceed or shift to achieve equilibrium. So if the trial KEQ is less than the actual, then we have to proceed to the right to achieve equilibrium. If the trial KEQ is greater than the actual KEQ, then we have to proceed to the left to achieve equilibrium, okay? So I'm gonna take a look at the next page. I need to finish this. I'm almost done, okay? So let's go right here. And I'm gonna do number 1 with you. We've got concentrations of various substances, and they want to know the direction that we're going to proceed to get to equilibrium. They gave you a KEQ value. This KEQ value here, this is your actual KEQ that we're going to compare it with. So the trial KEQ is equal to the concentration of CO times the concentration of H2 raised to the 3rd power over the concentration of CH4 times the concentration of water. Okay, this is going to end up giving you 2.4. Now, since the trial KEQ is less than the actual KEQ, your 2.4 is less than 4.7. That means the reaction proceeds to the right to achieve equilibrium. Okay? then I have one more thing to mention and we are done, okay? We're gonna look at the addendum to Le Chatelier's principle down here. Partially alleviating a stress is based on more than one chemical concentration being involved in the equilibrium process. So if you take a look at the next page, equilibria that have one chemical concentration in the equilibrium expression completely alleviate any stress that changes that concentration. Okay, so if you take a look here, I'm going to highlight the liquid. That means that you have one chemical concentration in your equilibrium expression, which you do here. Okay, so that means you would have to completely alleviate that stress if there was any stress brought onto it. This one here, you have two solids. That means you have one substance in your equilibrium expression as well. So we have to completely alleviate that stress when it happens. So if you take a look down here at the quick check, you will notice that there is one substance in number one. So would we partially or completely alleviate a stress that changes the concentration of reactants and products? Completely. Number two has two, so this would be a partial. Number three has one, so this would be a complete.